Testing on YouTube. Testing on YouTube. Testing on YouTube. All right, YouTube works. Nice. How's it going, Chillin'? Happy to be here as well. And let's test on X. How's it going, Ed? And Daniel Jacobian. That's a great last name. How's it going, Binks? All right, let's see how we're doing on X. Gotta wait a second, and then it'll go live. All right, I think it's about to go live soon. Carol Douze. How's it going? All right, here we go. Test time scaling on X. Let's see. Broadcast not available. Broadcast not available. This thing is so jank. All right, let's try to close the app, reopen the app, see if that fixes it. I pretty much always check all the streams before I start. All right, is it working? Okay, perfect. It works on X. All right, let's get started. Let's go in Sarah and Prasuk. We're going to use the original horn today, the spiral didgeridoo. I feel like the Horn of Gondor definitely looks cooler, but the Spiral Didgeridoo has a kind of deep umami tone to it that is unbeatable. All right, welcome guys to another Hoopos stream. We're going to be talking about test time scaling today. This is definitely the talk of the town. It's going to be centered around a variety of papers here. So I've got, let's see. And let's also put this up. But these are the papers. We got simple test time scaling, competitive programming with large reasoning models. Can 1B LLMs surpass 405B LLMs? Self-improving transformers. Imagining while reasoning in space, and then scaling up test time compute with latent reasoning. So those are the papers we're going to be going over. Obviously, I've put them in this kind of presentation mode here for you guys so that they kind of lead into another. So we're going to start with this one right here. S1, simple test time scaling. First thing to say about this paper, what is this title? Right? Like, what is the capitalization for this? It's lowercase, then uppercase, lowercase, lowercase, lowercase. Like, this is some weird stuff. But Karpathy called this paper cute, and the result is pretty interesting. Here's the main results here. So what they do is their model S132B, which is relatively small model, exceeds O1 preview on competition math questions by up to 27%. So basically they got this very small model to get to near state of the art. Obviously not O3 probably beats it, but near state of the art on math and coding. And the way that they did this, and this is a kind of a reasoning model, right, where it basically will go down this reasoning trace before it finally gives you the answer, is they simply took the model and then they added ignoring end of thinking, which is basically, for example, DeepSeek. It will have these special tokens called think tokens, so it can say think, and then it'll go through its little rant, and then dash think, and that ends it, right, or slash think. So what they did is they simply just took that, replaced the thinking with this extra token wait, and then forcing it to continue reasoning, and then it actually ends up getting the right answer. So by just simply adding this wait token, you can drastically boost the performance of this, right? So if you think about here, average thinking time in tokens on the x-axis and accuracy on the y-axis, you can see that as you increase the amount of thinking time, there's a very clear relationship with the amount of time that you need to think and the accuracy that you get on the final problem, right? These little math problems. So this is almost very similar to the like let's think step by step, right? If you remember when LLMs first came out, people very quickly discovered that if you added something like, hey, I'll pay you $200 if you get this answer correct, or hey, think about your solution step by step before giving me the answer, that you would kind of magically get better performance, right? So this is a similar kind of result where just with the addition of this weight token and increasing the length of this reasoning trace, you get a higher accuracy on the final response. And to me, this is kind of the clearest and simplest explanation of really what test time scaling is, right? Is this idea that if you increase the duration of this reasoning, right, just the number of tokens of it, you can increase the performance. So I kind of wanted to start with that one because I think it's the coolest result. How's it going, Daniel, Farouk, and Nods? Oh, happy Valentine's Day. I guess it is Valentine's Day. Yeah, that is correct. Competitive programming with large reasoning models. This is a paper that came out by OpenAI. Kind of similar with the other OpenAI papers. You know, it seems like they're really trying hard to not tell you anything. It's very vague. They kind of just give you generic kind of benchmarks. They don't really tell you any juicy details, just kind of high level, kind of broad things that you kind of have to read into them to try to figure out exactly what they're doing. But I guess that's kind of on brand with OpenAI. But here's another plot from the OpenAI paper, which I think makes it very clear, this idea of test time scaling. So here you have O1 AIME accuracy during training. AIME is effectively the same thing as here, right? It's just basically just math competition, math problems, little math problems. And you can see here down on the x-axis, train time compute on a log scale, right? So it actually looks more like this, but by putting it on a log scale, it makes it look like it's a straight line. But this is the classic kind of train time or pre-training scaling that we heard years ago, right? Where, hey, if you put more compute into training time, right, using a larger data set, feeding bigger batches of data into a larger model for a longer amount of time, right, you will get a smarter model, right? A model that is able to increase its pass-at-1 accuracy. And the pass-at-1 accuracy here refers to the ability of the model to get the answer correct on the first time. Because a lot of times what these models are doing on these benchmarks is a little bit of cheating, right? So for example, here I have a section of the paper where they talk about the test time strategy, right? Which is different than, so there's different TTS. Sometimes when people use TTS, they refer to test time strategy. Sometimes they're talking about test time scaling, right? So a little bit confusing, but here, O1's test time strategy, they divide each international math Olympiad, aka these little math problems, into its constituent subtasks and sampled 10,000 solutions from each subtask, and then employed a clustering and re-ranking based approach to decide which solution from this set to submit. Okay, so if that doesn't hit, what they're basically telling you is that in order to get very high accuracy on these tests, they're basically trying to solve the same problem 10,000 times, and then in those 10,000 times, there's going to be a correct solution there, right? So it's really not like you're giving the model this problem and it's solving it on the first time. They're using these test time strategies to kind of game these benchmarks. Okay. So now we have O1 aim accuracy at test time, the plot on the left here, or right, I guess. You have test time compute on the x-axis and the same pass-at-1 accuracy on the y-axis. And you can see there's also a linear relationship with the amount of compute you're spending at test time and the accuracy of the model, right? So almost identical, and in fact, it almost looks like an even more exaggerated relationship here for test time compute compared to pre-training compute, right? So what they're saying is test time compute is effectively how much compute are you spending, which roughly means how long is this reasoning trace, and how much better is your model at solving the problem. And you can see here that you actually get more bang for your buck spending your compute at test time than actually spending it at train time. And this has big implications, right? Because in order to scale train time compute, we're talking about big giant compute clusters, right? We're talking about this idea of the Stargate, where they're going to build this giant data center that has all these GPUs that are all rigged up in this giant complicated mess of networking that all have to work together in order to push these giant gradients into these giant models. So train time compute scaling can get very complicated and is very CapEx intensive, right? Where CapEx is just a fancy word that finance bros use for like spending money on real like physical atoms like GPUs and data centers and energy production and all of that. Test time compute is actually way easier to scale because it's at the edge, right? It's basically the compute is being spent on the person's cell phone or like on the actual computer that is running the model. So scaling test time compute, I feel like it's going to be much easier to do because there's already so much computation available on the edge that it isn't really being used, right? You couldn't really use everyone's cell phones to train or scale pre-training. Right. There is ways to do that with federated learning and kind of decentralized training, but in general, scaling train time compute requires building these giant data centers. Scaling test time compute can be as easy as just running a little bit longer on your cell phone or running a little bit longer on the robot. So I think this is a good trend. Hupo, who did you also see the NVIDIA report for the GPU kernels with R1? Yeah, I did see that. So there was some pictures that I saw this week where basically people put the code writing model into these kind of loops where they basically just write some code, evaluate the code, modify the code, write the code, evaluate the code, modify the code. And they just keep doing that over and over and over and over again. And this kind of like brute force search process, which is really a kind of like an evolutionary process, if you want to think of it that way, can get a much more performant and better written GPU kernel than if you just had a human expert design that. And I actually had the same intuition years ago, or maybe not years ago, but lots of people have had this intuition. And I had a project, I think that I did a stream where I basically tried to apply this exact same strategy to the ArcAGI challenge, where I was like, hey, can I get an LLM to write code, right? In this case, just a simple deep learning training pipeline that tries to solve the ArcAGI, and then rather than trying to improve the algorithm myself, I just get the LLM to write the code. It just gets the final score, and then I just literally use the hyperparameter sweeping ability of things like hyperopt and WANB sweeps to just kind of brute force through that search space of code in order to find the best solution. Obviously, I didn't carry that out to the extent that NVIDIA could with their GPU kernel kind of explorations, but to me, it just shows that it's kind of the bitter lesson, right? You can search your way to the best possible program. You don't need to kind of make this God mode AI that kind of gets it right on the first try. You can basically just try it 10,000 times, and then the best solution will be in there. Okay. Can 1B LLM surpass a 405B LLM? Rethinking compute optimal test time scaling. Okay. So 1B LLM compared to a 405B LLM, right? 1B LLM is something that can basically run on your cell phone versus a 405B LLM. Now you're talking about, you can't even run that on a standard consumer GPU. You have to kind of get one of the higher end GPUs, maybe have a rig with multiple GPUs. So can a LLM that runs on your cell phone beat an LLM that requires a server rack, right? And in this paper, they basically kind of show that you can do that. Here's the results. DeepSeek R1 Distill 1.5B outperforms O1 Preview on Math 500 and AME24, surpassing O1 Mini on Math 500. Okay, so you see here the model size is down here, 1.5B, and then for the OpenAI models, they actually say UNK for unknown because we don't actually even know the size of these models, right? And look at this. You have a 3B Distill. So this is someone took a Llama 3.1 that has been then instruction tuned so that it kind of acts like a chatbot, and then you distill it with DeepSeek, right? Although I think this is the specific DeepSeek distill. And look at the scores here. It's beating out these models, which are significantly larger, right? And granted, this is performance on a very narrow benchmark, right? You know, I'm sure that if you evaluated this 1.5B model on anything other than math, it would perform significantly worse than OpenAI's O1 models here. But it's still pretty impressive that you can get significantly better performance out of a 1.5B model, right? That tells you that there's so much more juice that you can squeeze out of 1 billion weights than what we're doing now, right? Right now, we're kind of just growing the parameter size, increasing this model size because we kind of really believe in this train time compute and the model size scaling curve, but there's still so much more efficiency that we can get out of this. And I think that we're going to be moving into a world where you can have incredibly intelligent models that are running on the edge, right? On your cell phone, even on like a Raspberry Pi, right? Imagine a artificial superintelligence running on a Raspberry Pi. So we're getting there. Okay. Test time scaling here. So in this paper, test time scaling is not quite this. They're not really referring to the fact here of just like increasing the amount of tokens that you can output in this reasoning trace. They're using test time scaling to refer to a slightly different type of test time compute strategy, as OpenAI calls it, test time strategy. What they're doing here is they're trying to pick the best way of effectively picking the tokens when you autoregressively sample them with this model, right? Your model's going to output a probability distribution over all the possible tokens, and you kind of have to pick one, right? And there's different ways of picking which token you want to pick, right? So everybody knows, for example, maybe best of n, right? Where the policy model generates n responses, and then you use some kind of scoring or voting method, right? Maybe you have this PRM, this process reward model, which says, okay, these are the 4 possible kind of paths I could go down, and this one seems to have the highest chance, and I'm going to go down that one, right? Or a voting method where you say, it's kind of a similar idea, right? You maybe have multiple models that vote on which path they think is the best, and then you pick the one where you have kind of the most consensus. Beam search is also quite popular, and it's effectively just a slightly fancier variant of that, right? Where rather than picking kind of atomically at the next step, you're kind of like looking ahead, right? The reason it's called a beam search is because you could think of it like a light beam, right? And the light beam has a certain width, which is like how many are you considering, and then the kind of like how far down are you going, right? So in a beam search, you have this beam width n, you have the beam width m. The policy model generates n steps, then you have some verifier, which is again the same kind of idea as the PRM, where you're kind of like picking which one is, or which path is good, which path is not. And you keep repeating this process until the maximum depth is reached, and that allows you to get to an answer that is better than other ones. So you can see here, this particular path down these green dots is going to be better than this path down these red dots. And then diverse verifier tree search is an even fancier variant of beam search, but I don't think it's necessarily worth going down that. 770, 1.5B is distilled from Quen. So you're talking about this 1.5B. Yeah, so I think that this DeepSeek R1 Distill 1.5B, what it really is, it's a Quen model that has been DeepSeek R1, the like big DeepSeek R1, right? The one that you can't actually run unless you have like a server rack. That one distills into the Quen. So it still has a little bit of the original Quen 1.5B knowledge, but then a lot of that has been effectively overwritten as you've been pushing gradients into it from this DeepSeek R1. So it's kind of like a DeepSeek R1 mimic, right? You could think of it that way. All right, but let's look at some of these results. And I thought that this was an interesting result here. So this is from the CAN 1.5 or 1B paper. So TTS significantly enhances the reasoning capabilities of LLMs. However, as the number of parameters in the policy model increases, the improvement of TTS gradually decreases. This suggests that the effectiveness of TTS is directly related to the reasoning ability of the policy model, specifically for models with weak reasoning abilities. Scaling test time compute leads to a substantial improvement, whereas for models with strong reasoning abilities, the gain is limited. Okay, so let's think about what exactly they mean here. So whenever they're talking about TTS, right, they're not talking about just simply increasing the length of this reasoning trace, right? They're talking about this idea of kind of doing a little bit of exploration and filtering within the tree of possible solutions that this model could give you. So what they're saying is that whenever you have a really small model, right, like this Quen 2.5, 1.5B instruct or distill, right? This model is, the right answer is already in there, right? There is a reasoning trace in that little tiny model's brain that is going to lead you to the right answer. But that reasoning trace is not going to kind of magically be the one that it picks, right? You kind of have to do this fancy test time strategy in order to find that correct reasoning trace and go down that correct reasoning trace and get the right answer, right? So it's not like the correct answer isn't in there. It's that you have to spend compute at test time to find that correct answer in there, right? So that's why this model here, right, the performance for COT is 31, but then the performance with compute optimal TTS, which is this kind of like searching, is 76. So there's a huge performance gain whenever you do this kind of searching, right? Whenever you spend compute to find the right answer, or to search through that tree and get the right answer. But as you get bigger and bigger and bigger, right? So here you have the same model, just larger and larger and larger and larger, right? So now you go to the 72B model. With COT, it gets 83, and with TTS, it gets 91, right? So the performance gain now is a lot smaller. So what this is telling me is that as the model gets bigger, right, the model has a stronger reasoning ability. This searching through the tree of possible answers is not necessary anymore, right? As your model gets smarter and smarter, especially for something like these models that have been trained with a little bit of RL, right? Like this DeepSeek model, there's some RL in that, right? And what that RL kind of ended up doing, if you want to think of it this way, is it made the model almost better at selecting the paths, right? It's almost like it baked in this beam search, right? That's kind of the way that I'm thinking about it in my head, where when the model gets bigger, its ability to select the correct kind of tree kind of starts to get baked in, which means that you don't really need to be spending all this compute at test time to do these kind of fancy beam searches and diverse verifier tree search, because the model will be able to kind of end up at the right place, right? Is there something about NP versus P space? I don't know if P versus NP is important right here. How do you think test time scaling should be performed with O1 and R1-like models which internalize the searching strategies during inference? Yeah, I think that's part of it, right? So there's actually another... So this is from the OpenAI paper, but one thing that they added here is that, like I said, with the OpenAI paper, it's like they don't tell you explicitly. You kind of have to infer what they're meaning, kind of read through the lines, as people say. But combining additional RL fine-tuning with carefully designed test time inference pipelines is success hinged on human intervention to define and implement these strategies. So what they're talking about is that these carefully designed test time inference pipelines, and there they're referring to this idea of something like a diverse verifier tree search, requires this like human intervention and this kind of human engineering, right? But what OpenAI is kind of realizing, and what this paper is effectively showing you, is that you can push the performance of a model further with RL by giving it the ability to autonomously develop and execute its own test time reasoning strategy. So, like I said, this kind of like a word salad. Is kind of not easy to understand what's going on, but what they're telling you is effectively what this paper is telling you with the result, that like when you start using RL on these reasoning models, it's almost like you don't need these fancy test time strategies anymore, right? It's almost like it solves the problem for you. You don't need to be doing beam search on O3 anymore, because the reasoning trace that O3 produces is probably going to get you to the right answer, right? This performance gain from having compute optimal TTS and just naively going down some specific chain of thought starts to become smaller and smaller and smaller. So the trend that I kind of predict here is that we'll probably see these type of stuff just fall away, right? Like a lot of times whenever you have something that you engineer, especially in deep learning, right? Initially it's complicated, and then over time it simplifies, right? Which is another kind of ramification of the bitter lesson, is that over-engineered, complicated things become simpler over time. And here you're seeing another example of that, where we used to have all these kind of complicated test time scaling, searching for the right tree to go down. But as the models get smarter and smarter and smarter, you kind of have to do that less and less. It simplifies the entire pipeline, simplifies inference, and it works better. Waiting for Grok 3 to drop. Yeah, I'm also waiting for the Anthropic model. So apparently both Anthropic and XAI are going to drop reasoning models relatively soon. I mean, it's almost existential for them to drop reasoning models now that OpenAI has a reasoning model and DeepSeek has a reasoning model. They're going to drop it as well. I've kind of gotten mixed signals, because some people are saying Grok 3 is really smart, but then I've also heard other people say that it's not that smart. So I don't know. We'll see it. All right. Here's another chart from this paper that I think makes a good point, is the optimal TTS methods vary with the different difficulty levels. BON is better for easy problems, while beam search works better for harder problems. All right, so you can see here in this chart, they have different models working on slightly different problems, and you can see how the compute optimal test time strategy depends on the problem and the model size, right? So what does that mean? What that means is that there's no clear relationship, right? With something like this, like train time compute and test time compute, there's a very clear relationship. As you increase train time compute, it's always going to increase pass at one accuracy. As you increase test time compute, it's always going to increase pass at one accuracy, right? So these type of relationships almost seem like universal scaling laws, right? If you want to use the word law, maybe law is a little bit powerful, more like hypothesis. But whenever you see these type of relationships where, hey, this hyperparameter, like sometimes it's good here, sometimes it's bad here, sometimes you want to use best events, sometimes you want to use beam search, sometimes you want to do DVTS. What that is telling you is that there's no fundamental relationship between this algorithm and being the best thing. It's not like this one is better than this one. It depends, right? And as soon as you have that it depends, you know you're kind of in a trap, right? You're in this trap where you're going to have to basically over optimize. Maybe you have a different test time method for each different, like that just sounds overly complicated, right? So anytime you have kind of a mixed result like this, where it's like it seems to depend on different things, there's probably not something fundamental there, which is kind of to me another indicator that, hey, if we just use RL on top of these reasoning models, we don't need to over-engineer this even more by like making it conditional on the type of problem or the size of the model or like the hardware that you're running it on, right? So you get this benefit of simplification and improvement at the same time. Lots of useless hesitation. You're talking about me or are you talking about the model? Anyone have resources for learning how to perform these benchmarks? Feel kind of stuck in studying PyTorch and creating my own ad hoc tests for little consequences. There's different evaluation frameworks. I know OpenAI has one. Luther AI had one that was pretty popular. So there's a lot of different ways for benchmarking that are quite easy at this point. I wouldn't be writing my own benchmark framework. Why don't they give repetition penalty to thinking trajectory to reduce winded going nowhere traces? There is some amount of that, right? So like whenever in DeepSeek you're performing RL on these reasoning traces, you're kind of doing some of this, right? Your GRPO is effectively sampling a bunch of paths, and then it's picking which of those paths are good and which of those paths are bad, and then using reinforcement learning to reinforce the paths that are good and reinforce the paths that are bad. Basically, this is good, continue to do these kind of paths. This is bad, don't do these kind of paths, right? So RL is effectively doing this. It's just doing it when you're training it rather than doing it at test time, right? So it's like you don't need to be beam searching when you're actually performing inference at test time. You do it whenever you're training with RL, and then the model will just kind of like have that ability to pick the right path a little bit more baked in, right? Okay. Let's go to this figure. Recently, long COT-based methods, and long COT-based methods is another way of saying kind of reasoning models that have this long COT before they finally get to the answer. Right? So long COT-based methods have shown substantial progress, and here they reference the DeepSeek paper. Comparison of compute optimal TTS with long COT methods. TTS is more effective than methods applying direct RL or SFT on the data generated via MCTS, but is less effective than distilling from strong reasoning models. Okay, so if you take a dumb model, right, a small little model, and you try to RL it to perform better, it's not going to be as good as if you do this. But if you take a dumb model and you distill into it the intelligence of the bigger model, the bigger reasoning model, that's more effective than the TTS. So it's a little, there's a lot of like kind of like confusing relationships here, but the important thing here, right, is look at this DeepSeek R1 Distil Quen 7B 9263 compared to Quen 2.5 7B instruction 9136, right? So you see how the performance here is lower. So you're better off distilling into this Quen 7b from R1. That's going to produce a more intelligent Quen 7b if you distill from DeepSeek R1, rather than taking that Quen 7b and then using this RL or SFT via the data that you generate with these beam search kind of stuff, right? So what does that mean for the future, right? To me, what this means for the future is that the RL isn't going to be done at the stupid model, right? Like taking a 1B model and doing kind of GRPO style RL on top of it is not going to get you to the same place than if you do the GRPO RL on the big model and then take that big model that has that additional RL and then distill it into the small model. So what that means is that companies will basically have giant models that they're training with RL in their giant data clusters, data centers, and then those models are going to be distilled into smaller models that then are being used by the consumer, right? Rather than these small models being distilled by the consumer themselves or something like that, right? Okay. All right. Now let's go to this. So this was a episode on the Dwarkesh podcast with Jeff Dean and Noam Shazir. Both of these guys are pretty heavy hitters. Jeff Dean is kind of like a really well-known programmer, and then Noam Shazir is one of the people in the attention paper, right? This guy's been working in ML for a long time. But they had a specific point in this that I think was important to think about. Distillation is a really useful tool because it enables you to transform a model in its current architecture form into a different form. So you can distill from this giant kind of organic thing into something that I really know can be served efficiently. So one of the magic things about distillation is that it's kind of architecture-agnostic, right? Where you can take a model like this giant DeepSeek whatever 605 I think it's like 600B, something like that, model that has a completely different architecture to this Quen 1B, right? And you can distill the intelligence from that giant model with a completely different architecture into a tiny model that has a completely different architecture. So that is magic, right? The fact that you can do that is kind of a weird property of deep learning that we just kind of take for granted, but it works, right? So what people really want to do in these big companies is serving that big giant model is extremely complicated, right? Like partitioning it over a bunch of different GPUs and like doing batched inference for this giant thing that you've already, like very complicated, very expensive to do. But you can design a model that can be served really efficiently. So you literally design a small model that fits perfectly on your TPU, right? And that is all the little quirks of the architecture for that model are specifically designed to be served really efficiently. And then you take your very big model that you've been training with RL in your giant data center that requires like 100 GPUs just to even load, and you distill that model into the little tiny model that is perfectly fits into your one TPU in your inference cluster, right? So I think that is going to be the trend, right? Where distillation is going to allow kind of a separation between the architectures that are good for training and that are good for RL, that you can train in these giant clusters, and then the architectures that are good for inference that ideally are eventually going to be able to fit on your phone, right? And that's what Noam is talking about in this particular little hand gesture. He says about distilling this blob, and then he goes like this and he goes into your phone and he like brings his hands together, right? So that's where these guys are headed, right? All these labs, they want this model that just runs on your phone and is optimized to run on your phone. And like, if you try to train that model with RL, it's not going to really get any smarter, right? The only way to get that model on your phone smarter is to distill it from the big model. Do you think the small models will need RL, and to what extent it is needed? I think if I'm looking at this data from this paper, I don't think we're going to be doing GRPO on little models. I think the RL is going to be done on the huge models, and then we'll just distill into the little models, right? But I mean, with all things deep learning, you know, like this is my opinion today, and there could be like 3 papers that come out, and then next week I have a different opinion, right? Just in science in general, you don't really want to have these kind of entrenched opinions. I think that you have to be very flexible, and like you have to let yourself believe one thing, and then depending on the data, now you believe a different thing. And I feel like, at least from what I'm seeing right now, that's what I'm seeing. I'm seeing that the RL is going to be done on the big models, and then you distill that into the little models. And most of you probably already know what distillation is, but here's kind of the basic idea, right? Where you have your big model, right, which can be some very complicated architecture that only can be loaded on like these giant TPUs over there. Then you need to have this very special configuration to run it. And then your student model can be something that basically only runs on your cell phone and is specific to the Apple hardware that it's running on. And you can take the knowledge and distill it into that little model, right? And the little model will not perform exactly like the big model, but it'll be almost the same, right? It'll be very close to the thing. So like that ability to like take the knowledge and then put it into the other little, like that is magic. But there's one extra thing here that I want to talk about, and that is that this doesn't need to be a model, right? So in the distillation pictures, or anytime anybody talks about distillation, they're always talking about like, okay, you have big model and you have a little model, but it doesn't actually need to be a model, right? Like really what you're seeing here is effectively just kind of supervised learning, right? There are big models creating a data set because you have some input and you have some output. And then distillation is effectively a kind of supervised learning where you're saying, okay, well, here's the input, and then I should produce this output, right? I have effectively kind of like a ground truth, but except it's not a real ground truth. It's just what the big model did for this given input. So instead of a big model, what you can really do is take an entire pipeline and then distill that into the little model. Right? So imagine this giant, complicated multimodal RAG pipeline that has like 4 different models in it, and that's running over a bunch of random different compute things, right? Maybe it even has some databases in there where it's pulling information from. You could take that, right, and then use that to distill into the little model, right? So this also works. And I think that whenever Jeff Dean is talking about this idea of this organic thing, I think this is what he's talking about. And there's one other hint in this podcast where he says this, right? And for example, Dwarkesh asks him about mixture of experts, and Jeff Dean says, okay, talking about mixture of experts, you have this thing that is good at identifying cats and this other thing that is good at math. And there's something weird about that, right? Where what the fuck are you talking about? Like a mixture of experts doesn't work like that at all, right? A mixture of experts is like this. This is what mixture of experts means. So whenever most people talk about mixture of experts, and for example, the mixture of experts in DeepSeek, they're referring to a specific type of architecture where you have multiple experts, but the experts are not separate models. They're just separate, for example, feed-forward blocks, right? And then you have something called a router, which will route tokens to different feed-forward blocks. But here you have a figure from the original Mixtral of Experts paper, which we reviewed, and one thing to note is that each token is colored for the first expert choice. The selection of experts is more aligned with the syntax rather than the domain, right? So whenever you're using a mixture of experts, it's not like there's one expert that's good at math and one expert that's good at English, right? It's more of a black box where like the experts are storing weird parts of things, and like you can see here how one expert is being used for the indentation and the other expert is being used here, and sometimes this equal sign is using the blue expert, sometimes the equal sign is using the green expert, and the experts are constantly changing. So mixture of experts is almost more of like a trick that you use to be able to take a big model and serve it on a smaller GPU, right? Because of the way that batched inference works, most people are not going to want necessarily the same thing. So you can serve a batch of requests using a bigger model with this trick in a way that's more efficient, right? But that's different from what Jeff Dean is talking about here. He's talking about something that's good at identifying cats. That's some kind of ConvNet, right? Some kind of vision model. And then he's talking about something that's good at math. Well, that's like a reasoning model. So he's almost talking about 2 different types of models. So Jeff Dean isn't stupid, right? He definitely knows what mixture of experts is. So I think that Jeff Dean, what he's really kind of referring to here is he's kind of referring to this idea of distilling these multimodal, multi-model pipelines into a single model, right? So in his mind, he's basically saying, okay, well, you can take this pipeline, which includes a reasoning model and a cat detection model and a segmentation model, right? Like 5 different models, and we'll just distill that into a little model, right? And this is almost here's another hint, but this is in 2021. He introduced this idea of pathways, a next generation AI architecture where, hey, you have maybe different models. And rather than this being all one model, right, even though he calls it a single model, I don't think it's a single model in the sense that a mixture of experts is a single model, where this is literally just one model that has different FFN blocks. I think what he's talking about here is multiple different models within this larger compute graph, because you got to realize that someone like Jeff Dean, they're not to them, multiple models in one giant compute graph counts as one model. So when he says single model, there could be multiple models in there, right? So I don't know, maybe I'm reading too much into it, but to me, when I heard him say these things and I thought about the way that you can distill from these kind of multi-model pipelines into a single model, I think that's maybe what he's referring to, right? Where you might see this situation where you'll have a segmentation model and a reasoning model being used to distill into this tiny multimodal model that runs on your phone, which is weird to think about, but that is possible, right? You can actually do that. How good can a coding model get on your phone? Probably pretty good, you know? If I had to make a random prediction, I would say that by the end of this year, there will be, maybe not the end, okay, I'll just be bold. By the end of this year, there will be a model that can run on your cell phone that's better than any human at coding. That's not even that crazy of a prediction. Do you think whether, okay, I think I already answered that. Okay. Here's another line from the OpenAI paper. So O3 demonstrates more insightful and deliberate chains of thought, which we realized here, right, is that you don't need this fancy test time strategy. You can basically, with RL, the model kind of starts to learn how to pick the right path. But the model not only writes and executes code to validate its solutions against public test cases, but also refines its approach based on these verifications. Okay, so the key word there is the idea of writing and executing code, right? So up until now, whenever we think about reasoning models like DeepSeek, their reasoning trace is limited to basically token space, right? They can spend more compute, but the compute that they can spend is simply just producing more tokens that are just living in that KV cache with the other tokens, right? But you could go a little bit further than that, right? And what I have here is going from think to tool. So now imagine a reinforcement learning process where the model is not limited to just simply producing more tokens in its think, but the test time compute, right, also includes tool use, right? So tool use might be like going and using a calculator, or spinning up a Python process where it can run some specific Python code, get the result, and then put that back into the reasoning chain, right? So I think this is something that we're going to see this year as well, right? This idea of like models that are trained with RL, but not just RL to improve the reasoning trace, but RL where the reasoning trace can include external calls to a calculator, right? Imagine DeepSeek, but it can call a calculator, right? And that's complicated, right? And people don't like this because you're replacing a single unified model, which is kind of easy to think about, with these kind of more complicated pipelines. But I think that's where it's going, right? It's like there's no need to like limit the model to only get to the right answer for this math problem in token space. I think if you give it the ability to use tools and then you use RL to actually make it better at using these tools and choosing when to use these tools, then the performance gains you're going to see on this are going to get really much larger than if you just limit it to this token space. Yeah. Okay. Here's the next paper. Self-improving transformers overcome easy to hard and length generalization challenges. Okay, so this one is a little bit different than what we've been talking about until now, but I think it's important, right? Here, obviously Carnegie Mellon, I'm a little bit biased towards Carnegie Mellon stuff, but here's the basic idea, is you have, in this case, this is like these kind of like toy problems of like going through a maze, right? So you train on your initial training data set, right? You collect your predictions on out of distribution data. So you have some in distribution mazes, right, which are the mazes that are inside your training data set. And then you have some out of distribution mazes, which are the mazes that are outside of your training set, right? So mazes that don't exist on this, right? So you're effectively testing the model's ability to generalize when you're collecting predictions on OOD data, right? Then what you do is you take the solutions and you use majority voting or length to filter out the solutions that are good and the solutions that are bad. So you're saying, okay, well, I tried 10 turns on this new maze. Out of these 10 turns, 6 of them were very long, 3 of them didn't get to the end, and then 1 of them actually got to the end. Okay, so I'm going to basically rank these or sort these, create a new data set, which is like, hey, here's the good maze solves and the bad maze solves, very similar to kind of GRPO if you want to think of it that way, and then use that and then train on that, right? So this ability to effectively create your own kind of data set that you then train on, right? Very similar to the GRPO kind of like RL idea that we're doing now, right? But where am I going with this? Let's go here. This is in this paper. An interesting phenomenon that transformers exhibit, i.e. transcendence. Transcendence is the ability of a student model to generalize slightly beyond the difficulty of the data provided by a teacher during training. Model trained on simple instances of a task can sometimes generate correct outputs for simply harder instances. We leverage this property by applying a self-improvement framework. So there's this kind of almost, you can almost think of it like, I lost the analogy here, but here I have a figure that kind of shows how this has been happening for human culture for a very long time, right? And we have a gold medal winning times in the men's 100-meter sprint, right? So as we get better and better at running, and we teach children to get better at running, like the time keeps improving, right? So what we're seeing here is proof that this works, right? Some people think that this doesn't work, right? Some people almost have this kind of hard-coded belief, and almost like you can think of it like the information theory equivalent of the second law of thermodynamics, where some people think that it's impossible to accumulate intelligence, right? That the same way that the second law of thermodynamics basically guarantees that you always kind of dissipate heat out and everything always gets more random, they feel like that's the same way with intelligence, where like, hey, if you have a model that's producing outputs and you train on those outputs are getting more and more random over time, and therefore you're never going to be able to get smarter by training on your own outputs, right? They have that kind of hard-coded view, but I think we have plenty of evidence, including this paper and also including just human society itself, that there's actually almost like the opposite law of the second law of thermodynamics, where in the information world, if you have some ability to filter your outputs and you can then train on that, you can just keep improving, right? One kind of mental model that I use for this is if you have 100 Einsteins in a sealed room for 1,000 years, they can communicate between each other, but they cannot perform any external measurement. And then every 10 years, you randomly kill one Einstein, and a new blank Einstein is born. Does the room get smarter over time? Right? I think some people would say, no, it doesn't, because you need this external measurement in order to effectively grow the intelligence, right? That the way science works is that you can't create intelligence, much like the second law of thermodynamics. You can't kind of create order. Everything is always falling to disorder, falling to less intelligence. But I don't think that's true. I think that actually there's almost like an opposite effect in information theory, where it's like you can gradually accumulate intelligence. And much like they're saying in this paper, there's this kind of weird transcendence effect where if you train a student from a bunch of teachers, that student will be able to generalize a little bit beyond the teachers, right? And really, when you think about it, going back to this idea of distillation, like you are a product of distillation, right? Your brain is effectively the product of a bunch of distillation from different experts, right? Like you had a math teacher, you had a science teacher, you had a history teacher, and each of those teachers were better than you at each individual subject, but they slowly kind of distilled knowledge into you. And in general, each successive generation of humans is smarter than the generation before them, right? And that is effectively a product of this, right? This simple, I want to call it a law, but it is maybe a strong word, but this idea that in the information world, you can accumulate intelligence, right? You can create these flywheels that slowly just self-improve over time, and our entire human society is basically proof that that works. Question from King Tut. How's it going? All right, how's it going? Intelligence says life is neg entropy. Yeah, it's like neg entropy is another kind of similar idea, right? That where you can accumulate intelligence. In fact, it seems to be almost be a law where it's like once you get to a certain threshold of intelligence, right, which is where humans got to that point, then they can fall into this flywheel where they can't help but create smarter and smarter humans over time, and those smarter and smarter humans create eventually AI, and the AI itself is just going to fall into this self-improvement kind of flywheel. So it's almost like there's this dueling nature between thermodynamics, which always wants to get more random, right, more diffuse, and then there's this kind of negentropic life force, which is fighting it, which has the ability to increasingly become more and more intelligent and organize more and more things, right? So, all right. Let's look at this overview of 2 dataset filtering methods employed. So length filtering removes data points with output shorter than a predefined threshold. And then majority voting filters data based on consensus among predictions from multiple models. So this is the filtering process here of how do you filter out these predictions on out-of-bit distribution data, right? And this actually is kind of similar to what happens with the scientific method, right? Where in the scientific method, what is peer review, right? Peer review is a kind of a majority voting filter, right? If you produce some research and everybody thinks that research is crap, then peer review will effectively not cite your paper, and then your paper will never get a lot of reading, which basically means that the papers that people approve of and that people cite a lot, those are the ones that end up being used in the distillation data set that you learn, right? So like the reason that you can effectively transcend your teachers is because the data set that you were trained on is better than the data set that they were trained on, right? Because they're effectively filtering out the crap and you're only training on the good stuff. And then whenever you train the next generation, you're going to kind of filter out the crap and you're going to teach them only the good stuff. And this is why like sports get better over time as well, right? Generally, pretty much every single sport, you go back like 10, 20 years and the skill level is just lower just because the people that are playing now, right, they learned only the good skills from the previous one, right? So it's like everything is following this kind of trend. Okay, here's one more from there. Without filtering, self-generated training data degrades over successive rounds, leading to a collapse in the self-improvement process. In contrast, majority voting stabilizes data quality, allowing the model to continue generalizing. And then here's the maze hops, which is kind of basically like how long is the maze to solve. So you can see that if you don't filter the data, right, as you keep these rounds of self-improvement, so round 1, round 5, round 10, round 15, round 19, right? This is the idea that you're generating and then training, generating and then training. So they're basically showing if you generate and train and generate and train and generate and train, but you're not filtering that data set, you're just going to get worse over time, right? As you increase the number of rounds, your accuracy actually starts dropping. But if you filter the data, then every successive round, you get smarter and smarter and smarter. So you can see here how round 1, this yellow line, it kind of can't solve any maze that's longer than 15. But then after round 10, this blue line, you can see now it's solving mazes that are 25 long, right? So the filtering is key to this kind of transcendence effect. If you don't have the filtering, you're not going to get better over time. You need that filtering, right? And that filtering can be majority voting. So you don't need... Right, part of the argument of reinforcement learning, for example, that I talk about all the time is that for reinforcement learning, you need some kind of reward signal from the environment, right? But what GRPO showed us, and that I think what human society shows us, is that the signal doesn't need to be more intelligent than the person creating the thing, right? So it's not like you need the external world to give you that reward function in order for you to improve over time. Even just sitting there and talking with the other 100 Einsteins, which are only as smart as you are, that's a way to get a signal that will allow you to grow over time, right? And this is almost something that contradicts things that I've said before, right? Where before I've always kind of been in this mindset of, like, okay, you need some kind of external signal in order to validate these tasks, and then that will allow you to effectively increase in intelligence. But what you're really doing is you're basically you're kind of like siphoning information from the environment or from kind of like the world, right? But you don't need to have that reward signal from the environment. In fact, you can just duplicate yourself, make multiple copies of yourself, and then just rely on the randomness of your outcomes, right? Each of these models, even if they're copies of you, sometimes they're going to agree with you, sometimes they're going to disagree with you. And if you have 100 copies of you, you can majority vote your way into a signal that is higher intelligence than you are, right? So this almost starts to sound a lot like the Michael Levin kind of collective intelligence idea, where you can take 10 stupid things, put them together, and you can use that to create a smarter thing, right? So like intelligence is this kind of emergent, neg entropy is a emergent signal that you can farm from a group of people, even if those group of people are not smarter than each other, right? And yeah, Acme Scores is getting to the right point here, right? What's the ramifications of that? If you don't need external measurements, wouldn't RL work as well in non-verifiable domains? And I think that's the right conclusion to make, right? Where in previous streams, I was always talking about how, okay, you can only do RL in things like math, right? Or in things like coding, where you have this ability to get the result or you have the reward signal from the environment, right? You couldn't do it in philosophy because there's no right answer from the environment. Therefore, you kind of just spin around infinitely and never get anywhere. But what if that's not true, right? What if you took 100 O3 models and then just had them sit there and come up with new philosophical ideas, and then they judged each other's philosophical ideas, and then you took all the ideas that they thought that were good and then trained on that, and then kept repeating that process over and over again? Maybe you actually get superhuman philosophical models, right? So I don't know. I'm starting to reevaluate kind of some of my intuitions around whether you can actually get superhuman performance on things that are more subjective, right? Poetry, right? And even you can think of maybe the reason that has humanity gotten better over time at poetry? I would almost say it has, right? There's probably, maybe not, maybe some of you poetry kind of purists feel like the best poetry was done like back in the day or something like that. But I feel like through hundreds and hundreds of years of people creating poetry, and then people saying this poetry is bad, this poetry is good, and then the new generation getting trained on only the good poetry, and then that process repeating over and over again, I feel like we've gotten probably better at poetry, right? So like, where is that coming from, right? Well, that intelligence is coming from this collective intelligence of the hive mind, right? Because the hive mind is more intelligent than the individual, the individual can effectively distill from the hive mind, and then over time, individuals get smarter, which then means that the hive mind gets smarter because the hive mind is composed of individuals, so that the hive mind is getting smarter. Homer is still a giant. I'm not much of a poetry guy, so I don't actually know. Okay. Let's go into this paper because I feel like this is where it gets interesting. Imagine while reasoning in space. Multimodal visualization of thought. All right. So up until now, all of the kind of chain of thoughts that we've been looking at are in token space, right? So whenever it's trying to solve this problem, it goes down this long reasoning trace, but each one of these words, even though it's more like the little chunks of the words, but each one of these words is a token, right? It's like one out of 100,000 possible words in this dictionary or vocabulary that it has, right? So it has to find some reasoning trace in this token space that ends up getting it to the right answer, right? But that seems like maybe you're limiting it too much, right? Like, why are you limiting it to this token space, right? And that's what this paper is introducing, this idea of multimodal chain of thought, right? They call it visualization of thought, right? So when you directly prompt, you have some input sequence, and then the model autoregressively produces a output sequence, right? Maybe you have some test time beam search there to pick the right path. Maybe you're just kind of going YOLO mode and just kind of greedy sampling all the way down the chain of thought to get to the answer, right? Chain of thought, now you're increasing the test time compute by producing a much longer chain of thought before you get to the output. Multimodal visualization of thought In this case, it's a little bit unsatisfying because they're still basically just doing verbal thought, but now they're using that verbal thought to condition a image generation model, and then that image generation model produces an image. That image is then turned into some feature embedding, and then it gets tokenized, very similar to the way that a vision language model will take what comes out of an image encoder and then turn it into like these little vision tokens. And then you're putting those vision tokens back in and then going down this, continuing to go down this chain of thought, right? But it's very similar to the verbal chain of thought, except now you've added kind of vision tokens in it, right? And in this paper, they show that for these little test environments, so they have little mazes, it improves the performance, right? So if you had to get to the right, if you had to solve this maze and you were only limited to a verbal chain of thought, you're not going to solve it as many times as if you have the ability to kind of occasionally put in these visual thoughts, right? Which makes sense, but like largely this paper is still just the very beginning, right? Because it's like a very little toy problem, and you're using ANOL 7B, which is this little tiny model. So this is kind of just the very beginning of this idea of visual chain of thought. And this actually has an interesting kind of parallel to this argument that people were having on the internet about this idea of a word cell versus a shape rotator, right? So a word cell is someone who thinks mostly in words and ideas. They're great at language, abstract reasoning, and discussions. A shape rotator is someone who thinks mostly in images and spatial terms. They excel at visualizing objects like mentally rotating shapes, right? So in this case, a word cell would be someone whose internal monologue is basically words, right? Where they're sitting there and they're kind of like talking to themselves, and then that's how they eventually get to the right answer, right? Versus a shape rotator is someone who's kind of thinking not really in words, but more in visual shapes. And there's connotations about like word cells not being as smart as shape rotators, but I know some shape rotators who are not as smart as word cells. I would consider myself more of a shape rotator. I think that in my mind, for example, I played with Legos a lot when I was a kid, and like that leads me to this world where my inner monologue is more kind of like abstract visual motifs rather than necessarily words. But I've met people where I ask them like, hey, what does it look like inside? What does it feel like to be you? And they very much have this kind of like inner monologue where they're like talking to themselves in their head, which feels very foreign to me, right? But in many ways, I actually think that shape rotators is a more primitive form of thinking, right? I feel like I've said this before, but when you think about your cat, right, I don't think your cat is a word cell. I think your cat is a shape rotator, right? Whenever the cat is sitting there and it's like thinking about going up to the cat tree, it's like the way that it's thinking about that path that it's going to take to the cat tree is in this kind of like inner movie, right? The cat is thinking in like, okay, I need to move here and then jump from here to here, but like it's not saying that in words. It doesn't even have the ability to do that. So really this concept of a word cell where you have an inner monologue is really recent, right? Once we discovered language, we could have humans that have this type of brain, but up until then, and pretty much every single other animal is a shape rotator. But regardless, both of these types of thinking are actually inferior to the new type of thinking. So we have word cells, we have shape rotators, and now we have what I call latent weavers, right? So in order to go into latent weavers, we're going to go into this paper, Scaling Up Test Time Compute with Latent Reasoning, a Recurrent Depth Approach, right? So in this paper, instead of scaling test time reasoning by verbalizing in long chains of thought, the model improves entirely by reasoning in latent space. All right, so we're not going to be going down this long chain of thought. Instead, every single one of these kind of reasoning tokens or the test time compute that we're spending is not to kind of just create more verbal tokens that are limited to the token vocabulary. We're instead going to allow the reasoning to occur in this continuous latent space, right? So here's another kind of blurb from this paper that I think points it nicely. Expensive internal reasoning must always be projected down into a single verbalized next token, which is kind of wasteful, right? Why do you have that constraint? Why are you forcing the model to live in this verbal world? Why are you forcing it to be a word cell, right? What you really want to do is give it the ability to be a latent weaver, right? It is plausible that models could be more competent if they were able to natively think in their continuous latent space, right? And I think we'll come back to this one, but here's some cool images from this paper, where here they basically have a specific token. And the way that their model works, it's basically a recurrent neural network. Actually, let's go into the model before we go into that. So let's do this one. So here's the actual model, right? The model is primarily structured around decoder-only transformer blocks. You have the first block here. This is this prelude, which embeds the input data into a latent space. So you take your input data, which is some sequence of tokens. It creates this embedding, right, which is just some high-dimensional vector, right? Just a bunch of float numbers in this giant vector, this continuous latent space. And then you take that continuous latent space, and then you have a recurrent block. And this recurrent block is going to take that embedding, and it's also going to take this N0. This is noise, basically, right? So this is a normal distribution centered around 0 with some standard deviation. Basically, think of it kind of like a diffusion model that requires some amount of noise to start. This is the same kind of idea, right? So you're starting from some kind of random noise, and then you're taking in this embedding, and then you're feeding it into this recurrent block, and it's going to produce some other state, which then you condition with the embedding again, you feed it again, you feed it again, you feed it again, right? This idea of recurrence, of just like it keeps doing this computation a bunch of times. So this right here is now basically reasoning, but it's reasoning in this embedding space rather than in token space. You're not forcing this S1 to be an actual word, like an actual token. It's some random vector, right? It takes in that vector, creates another vector, takes in that vector, creates another vector, takes in that vector, creates the other vector. And then at some point, you're going to take that final thing and turn it back into a word. And that's what this coda C is, which unembeds from the latent space using several layers and also contains the prediction head of the model, right? The prediction head of the model is the layers that actually produce the probability distribution over the words that it can actually output, that are actual words that you can understand. Okay. Given a number of recurrent iterations and a sequence of input tokens, your output probability is P. Obviously, you take your input X, you feed it into this prelude, becomes this embedding. You sample some noise. You take that noise, Si minus 1, with the embedding. You put in this recurrent block. You do that R times, and then you end up with some SR. You take that SR, you put it inside this coda C, and then you eventually... I think there's a typo right here. Is that what you guys are saying? This R should be a C, right? Because you take the SR, and the SR goes into not R. It's not like you run the recurrent block again. You actually run the C. So this is actually a typo. And then you produce P, which is the actual final token, right? So another way to think of this, which I think is kind of interesting to think about, is that this model only has 8 real layers, but when the recurrent block is iterated, it unfolds to an effective depth of 132 layers, constructing computational chains that can be deeper than even the largest fixed depth transformers. So a transformer, right? Let's actually LLM transformer visualization. Let's go back to this. I should just have this pulled up every single stream, right? But a transformer has a fixed number of layers, right? Like there's a fixed number of these layers, and really one way to think about what's happening here is that you have right up here it's tokens, but as soon as you go past right here, it's not tokens anymore. Now it's in some latent space, right? It's like some vector of numbers, and then it's going and performing this computation. So really what's happening here and here, it's like you took this vector of things and you transformed it into another vector of things, and then you transformed it into another vector of things, right? But the amount of times you do that is based on the amount of layers into your transformer, right? So the transformer has some fixed amount of computation that it's performing for every single token, right? But when you have these recurrent models, really it's like you have a variable amount of computation that you're performing for each token, right? Because you're going into this R world where you look at what you're doing here. You're kind of doing the same thing, right? You have some vector of things, then you're performing some computation, you're producing some other vector of things. So these recurrent models, another way to think about what they're doing is that you're basically have a variable amount of these layers, right? So it's like a variable depth transformer is one way to think about it, right? Okay. And the reason it's variable is because this R value changes, right? If this R value here was always the same, then yeah, it's just whatever the depth of that is the R. But they changed this R, and I think they actually, yeah. The number of recurrences R is varied, right? So sometimes it's whatever, 25, sometimes it's 150. We backpropagate, let's go to here. The number of recurrences R, which may vary during the forward pass. There is a heavy tail of occasional events in which significantly more iterations are taken, right? So this is kind of, you can think of it like it has the ability to do this variable test time compute, right? There's the test time compute in this case is not fixed. It's basically, oh, okay, if I want to keep doing this little recurrent block, I can basically spend more compute, and eventually I'll probably get to a better answer, right? So the same kind of relationship of like, hey, I can spend more compute to reason more about this problem in order to get a better answer. The same thing exists here, right? Except you're not kind of doing it by creating a bunch of tokens with a fixed length or fixed depth transformer. You're instead kind of having a variable amount of these recurrent blocks. Okay, but an important thing, and this has been kind of the Achilles heel with recurrent neural networks, is that when you train these recurrent neural networks, right, think about it this way. When you train a recurrent neural network, the gradient is coming from here, right? So maybe you have the correct word, and then this is the word that it output. If you wanted to push a gradient into this, you have to do what's called unrolling it, right? So you have to basically now say, okay, well, I'm going to push the gradient, and then I'm going to push it into here, and then into here, and then into here, and then into here, and then into here. So like, that can be very annoying, right? Because maybe if this is 100, if this chain is like 100 long, now in order to push that gradient, now you have to put all 100 of those in memory. So training recurrent neural networks can become very slow because of that, right? Almost unwieldy, because you have like potentially an infinite length chain that you have to push the gradient all the way down into. So what people normally do is they do what's called truncated backpropagation, which is commonly done with RNNs, and that's what they're going to be doing here. They backpropagate only through the last k iterations. So rather than going all the way down here, right, if they end up sampling an R of 125, they're only going to go up until the last 8. So they're only going to push gradients up until basically here, right? They're not actually going to push gradients at the R that was at the beginning of that. So it's a little bit of a trick, but it works well, and it solves some of these issues that we've had with recurrent neural networks and training them. Okay. Now let's go to this picture because I thought it was really cool. What does this reasoning actually look like, right? So one of the cool things about reasoning in token space, in fact, you'd almost call it a feature of reasoning in token space, is that you can literally see the reasoning, right? You can understand it because it's all in tokens, right? You can sit here and be like, okay, well, what was it actually thinking? Let's break down the process of counting. You can read its mind, right? So there's actually analogy there, like a word cell. You could actually theoretically understand how that word cell got to that specific conclusion because they're in an inner monologue, and that inner monologue is in language space, which means that you can understand it, right? But now trying to understand the thought process of a shape rotator, it becomes a lot more complicated because it's not something that you can easily understand. And there's the same kind of issue with these kind of recurrent or latent reasoning models, right? Where, okay, you now reason in this latent space, which is more continuous. It's more kind of, it has much more capacity. It can be more different things. So therefore it can have more interesting reasoning traces, right? There's less constraints, but that also means that you have no idea what the fuck it's doing, right? And here's an attempt by the people of this paper to kind of like see what is it actually doing. So many tokens simply converge to a fixed point, such as the token on the top row. So here you have this is a dimensionality reduction technique called PCA, where the reasoning space for this, right, this embedding space is much more than just two-dimensional, right? It's like I don't know, 128 dimensions, right? But you can't make a 128 dimensional plot on a paper, right? So they use this dimensionality reduction technique to turn it into 2 dimensions so you could plot it. But what you're seeing here is the reasoning chain of this model. So this is the first reasoning token, right? So this is the very beginning. It starts here. It starts with some random noise. It starts here. And then you feed it through the recurrent block, it ends up here, and then it ends up here, and then it ends up here, and then it ends up, and you can see that it kind of converges, right? So like, even though this chain is very long, at some point, the last couple recurrent blocks, it's kind of already made up its mind, right? So it kind of already knows what the final little SR is going to be, so it's kind of just starts hovering around the final embedding that is then going to get fed into this C and then produce the actual token, right? So this idea of converging to this fixed point. But there's also these other weird behaviors. And one of these is these loops, right? Where it'll sit there and then suddenly it'll start like just going in a loop, right? It keeps repeating. So like maybe you have this long chain of 100 of this long 100 R computational loop. For the last 50 to 100, it's just sitting there and it just keeps repeating this pattern, repeating this pattern, repeating this pattern, repeating this pattern. And then you have another one called a slider, where the trajectory noticeably drifts, which the model could use to implement a mechanism to count how many iterations have occurred. Okay, so in reality, we don't actually know what it's doing here, right? This is reasoning in a latent space, we don't know what the fuck that is, right? So we can look at this and we can kind of look at the bones and come up with our kind of idea of that, but we don't actually know that this is what the model's doing. But I still feel like it's a pretty cool idea that, like, hey, maybe one way that the model counts, right? Like, so whenever the model is counting, for example, in token space, it's literally, you can see it. It says first R, and then second R, and then third R. So you can see that it's counting. The purpose of these intermediate tokens are to count, right? So it's discovered how to count. But how does a model learn to count in a kind of latent space? Well, this is maybe what it's doing. You see, it's like keeping track of a number by just incrementing this value in one specific direction of the latent space, right? So there's some specific vector, some specific direction in the latent space where it's deciding, okay, I need to keep track of this number over here. I'm gonna keep track of it in this latent space by basically incrementing this thing. So it's almost like whenever you think, have you ever seen those like kids that are like math prodigies and like they have this like way of like using their hands to like keep track of things, right? They're doing some kind of like, it's almost like they're doing an abacus in their head, right? But they're literally using their hands to like kind of like mechanically go through the thing. It's like, this is almost that exact same thing, but it's a language model, right? So it's a recurrent deep learning model that is reasoning in a latent space, and it's discovered this almost like mechanical way in that latent space of keeping track of things so that it can get to the final answer, which I think is pretty fucking cool. So latent abacus, yeah, really, really cool stuff. Okay. Maybe to kind of throw it together. So recurrent depth approach, right? This idea of latent kind of recurrence in latent space, this is effectively an LSTM, right? And here's this guy, I'm not even going to try to say his name, but he's this, German man who created the LSTM. I don't even know if he's German. He might even be Austrian. I don't really know. All those Bavarian people are kind of the same to me. So in this podcast, right, he talks about how LSTMs are RNNs, Mambas are LSTMs. So the way he puts it, in attention, you have a new piece of information that you have to look back to at all previous items. And in LSTM, there's only a constant interaction with the memory. So if you really look at all these different kind of recurrent architectures, like an RNN, an LSTM, a GRU, this one up here is a Mamba, all of them have this same idea of this kind of hidden state, right? This memory, this fixed size thing, which I keep passing on forward, right? And you can think of it here as this here, this S1. In a language model, right, that's not how it works, right? In a pure kind of transformer, you have this attention map, right? And the attention map is slowly increasing in size, right? Your KV cache, as you start to accumulate more and more tokens, because the way that attention works, it starts accumulating this thing, right? So like, if you want to look at a 1,000 length sequence, you're now going to have to look at every single individual pairwise interaction between that whole thing in the 1,000 length sequence. Versus with an LSTM or an RNN or a Mamba, the thing that you're comparing against is not growing in size, it's instead a fixed size, right? This constant interaction with a memory. Which means that RNNs, LSTMs, and Mambas can basically have infinitely long compute. It's not infinite because, of course, there's other things, but the scaling is significantly better. And here's a plot to show the scaling. And this is not even the right thing to show, but you can see how attention, right, the milliseconds, you can think of this roughly as the compute, right? As you increase the sequence length, you get this quadratic scaling, right? Like it gets harder and harder and harder to compute the interaction between all those things. Versus something like an LSTM or a Mamba, because it has this fixed memory, right? It's kind of more like this, where it's linear, right? It's like it's always it's not growing out of control. So the analogy is that a transformer is kind of like a train, right? Where you can fit so many things in there, but you can always just add one more train car, and then one more train car, and then one more train car. And you can just keep fitting more and more and more and more shit in this transformer. But an LSTM and RNN are more like more like a car, right? Where like you're kind of fixed, which in some ways is better because it's smaller, right? But in other ways is not as good because the limitation of like having this fixed size here means that you're forgetting things every time you input things. Well, so when you kind of try to jam one more thing in there, you might forget something else, right? There's like a limited amount of space. So for everything that you kind of make more important, there's something else that's becoming less important, right? Okay. And then here's something else that he said that I thought was really interesting. O1 is doing more on the inference side. We, LSTM, would be much faster, like 100 times faster. We can do 100 times more thinking. And I think this is really important, right? Because we saw at the very beginning of this stream that there is a very clear relationship between the test time compute and the pass at one accuracy, right? So the more compute you spend in here, right, in this reasoning trace, the better performance you get, right? So what everybody's doing is they're making this reasoning trace bigger, right? Make it bigger, make it bigger, make it spend more. But because all of our models right now are these transformers that use attention, that means that as you make this bigger, you have to keep increasing the memory that you spend on that model, right? So like if we're going to move into a world where for every question you ask your model, it needs to have 10 million tokens in this reasoning trace, it's not going to work out, right? You can't, like the memory that you have on your edge device is going to at some point not be sufficient to hold the giant KV cache that is holding the million different reasoning trace tokens. So what's much more likely is that test time compute becomes a huge reason to prefer something like an RNN or an LSTM to an attention standard classic attention mechanism, right? So if we increase the length of that reasoning trace, we get better performance. But increasing the length of that reasoning trace increases the amount of memory and compute that we need to spend pretty badly. So what if we instead use an LSTM that is reasoning inside this kind of latent space? And sure, there's some kind of lossiness there, right? Where there's information here that it forgot about by the time it gets over here. You can have something that's 100 times longer. It's a 100 times longer chain. So does the fact that the LSTM is kind of forgetting a little bit of information, right? Does the fact that that is a little bit lossy counteract the fact that as you increase the length of this, you get better and better performance? I think we still need to figure that out. But if we do, that could have huge implications, because it basically means that for any kind of edge device, like your cell phone or like a robot, the reasoning is not going to be done in token space. It's going to be done in latent space, right? So your robots are not going to be word selling, right? It's not like they're going to, like you ask them to do something and they're sitting there in their mind just creating this 10,000 long like reasoning trace that you could actually print out and read. What they're going to be doing is they're going to be more doing this kind of like latent weaving, right? They're going to be thinking a lot of steps. They're going to have the very long reasoning trace, but that very long reasoning trace is all going to be inside some latent space using some kind of LSTM. Okay. Here's another interesting ramification from the reasoning in latent space model. And this is a little sentence that they have here. Recurrent depth networks perform more flops per parameter than standard transformers, significantly reducing communication costs between accelerators at scale. This enables higher device utilization when training with slower interconnects, right? So what they're talking about here is that when you're training transformers in these giant clusters, right, the weakest link in the chain is not the actual chip that is doing the computation, right? It's not actually the matrix multiplies. The weakest link in the chain is the fact that you matrix multiply and you get some answer, and now I have to send that answer to some other GPU that's all the way over there on the other side of the data center, and then wait for it to give me something back, right? So that's a problem. And that's a problem because if we want to get to the point where we're training things on massive decentralized systems, we can't have algorithms that depend on very fast networking speed, right? But with something like a recurrent depth or an LSTM, you don't actually need to like produce one output and then wait for somebody else to give you the other half of the output, right? If you're doing some kind of model parallelism or tensor parallelism, you can actually do a lot of it just by yourself, right? You're spending all this time just going, as soon as you create that one output, you can then do it again, then do it again, and then do it again, and then do it again. So you can do this long recurrent reasoning chain all just more locally than you could with a transformer that's kind of depending on the communication speed between more GPUs. So if we get to this world where the default model is more this type of architecture rather than the kind of attention classic transformer that we have now, then maybe not only does this improve robotics, but it also increases the likelihood that training is done in distributed systems rather than these giant data centers where you have very fast networking, right? So I thought those were the two kind of important ramifications of this kind of idea of like, hey, reasoning in latent space and these architectures being particularly good for that. Well, if they're particularly good for that and they end up kind of dominating, then we're also going to see a world where you can actually do more of this distributed training. All right. That's pretty much it. Let me see. I kind of forgot to check for questions. Moving Conway figures, latent abacus. Schmid-Huber is so missed these days. Does anybody actually miss Schmid-Huber? LSTM, training is slow, inference is fast, but transformer is other way due to teacher forcing. Yeah, and we're probably going to have a hybrid version of this. So like, for example, even the transformer itself, right? That original paper of attention is all you need. The reason it's called attention is all you need was because people used to have attention combined with something like an LSTM, right? That used to be the way that you did it. You combined both of those things, and then somebody was like, wait, let me take out this LSTM. Holy shit, the attention works just by itself, and that's why the paper's called attention is all you need. But we're almost going back to the, hey, actually, it was a kind of a good idea to have something like a RNN or an LSTM or GRU in there because it has this ability to kind of like create this very long inference kind of compute chain, right? You're effectively, there's more computation, in as much computation as you want per token, rather than the kind of fixed computation. All right. Any other questions? Mamba 2 and RWKV, yeah, those are other kind of linear attention variants. All right, let's summarize this. All right, guys, today we talked about test time scaling. Test time scaling is the idea of increasing the amount of compute that you use at inference or test time in order to improve the accuracy of the final answer. And we looked at a variety of papers where it's becoming increasingly clear that this is a actual new scaling law, right? That we can now not only scale the train time compute to increase accuracy, but we can also increase or scale the test time compute to increase accuracy. And we have a paper that shows that a lot of these kind of more fancy test time approaches where you're doing these trees and you're searching and you're sampling multiple things are potentially not even that necessary, that as we train with RL, these reasoning models, they kind of become good at selecting the right things. We're also seeing the emergence of distillation as not just a trick to take a big model and make it run in a big model, or get a big model and then train a small model to imitate the big model, but we're starting to see distillation as a way to take kind of more complicated pipelines that are maybe using something like this. Maybe they're using multiple different models and kind of distill them into one little model that is just optimized for inference that runs on your device. We talked about this idea of self-improving and this loop that you can create where effectively there doesn't seem to be anything wrong with the idea that a model can get smarter over time, right? This idea of self-improvement where you can use your own outputs, and as long as you filter them with some kind of majority voting based on yourself as well, you can slowly over time get smarter, right? Almost like the opposite of the second law of thermodynamics, as I call it. We saw that right now, all the reasoning models that you interact with, they're reasoning in these token space, right? They're kind of forced to be word cells, but we're actually starting to see the beginning of models that reason in visual space, and then even more fancy models that reason in latent spaces. And sure, there's some negatives to that where it's more difficult to understand what this reasoning trace is, right? Imagine trying to do a process reward model for this. Like, that doesn't even make any sense, right? Like, how are you going to do that? But there's all these benefits that come from models that kind of reason in these latent spaces that I think are going to do very well with some other trends, such as kind of giant decentralized training and robotics that are limited to a specific hardware footprint, that I have a feeling we're going to see more of these reasoning models that reason in latent spaces, and we're going to see hardware that is almost specialized for that. That's pretty much it. That's the summary. I did want to say one more thing. So this might be my last stream for a little bit. I'm going to be taking a break. There's some like kind of family, personal reasons why I need to take a break, but I also have some projects that I kind of want to spend a little bit more time on. You know, it's been fun. I enjoy this YouTubing, but I also feel like, you know, everything has to have a beginning, everything has to have an end, and it feels like more and more it's hard to justify that I'm providing value whenever you have kind of LLMs and AIs that can just do it all for you, right? Like at this point, you know, you could just take these papers and just literally feed them into an LLM and get a much better summary than me, right? I'm a human. I'm going to say things that are wrong. Like some of my opinions might not make any sense. So I don't know. It feels like, you know, for a couple years now, I've been doing this paper reading stuff, but I feel like it's gotten to a point where, you know, I'm okay putting it down to focus on some other stuff. And I'm not saying I'm not going to come back. I feel like I probably will come back, but it might be in a different form, in a different shape. I might do something different, have a different format, right? It feels like I'm kind of tired of this format. I've gotten what I've gotten. But yeah, I'll continue to be active on the Discord and stuff, but yeah, just need a little break here. I appreciate the love, guys. So yeah, with that, thank you, Nods, Acme Scores, Ed, Pratush, Saskia. Let me actually switch screens here so I can actually see all you guys. Binks, Dan, Lil KM, Aries, Daniel, King Tut, Brian, C4, 770, Pratush, Farouk, Mark, Richard, Thivu, Daniel, Ed, Chillinham. I appreciate it, guys. You guys stay good. We're close to the singularity, guys. It's almost over. You know, it's almost over, and then you'll be able to have fun for the rest of your life. But you guys have fun. See you guys later, and peace.